and welcome to the first session of the 2023 Storage Developer Conference. Thank you for coming to see me here today. Really appreciate it. Funny thing, I was presenting material similar to this, the Flash Memory Summit, about 5 weeks ago, and I came down with a case of pneumonia there, and actually just barely getting off of it now. I didn't actually come down with that at the conference. I think I got it right before I traveled, but so bear with me. I'll have to take gasps of breath to catch up with myself here. Okay, I'd like to talk to you today about E3 SSD design, maximizing capabilities, and what we're doing at IBM in that space. So I'm going to kind of go through what is EDSFF throughout this presentation, just bear with me. If you're not familiar with the standard, I'll get into some of the details as I go through. So why would we migrate to EDSFF? The Enterprise Data Center Standard form factor has a lot of good features. It gets rid of the old SATA style connector that U.2 had. It's very good for high amperage. It's very good for reducing the cost of your card. You don't have to go buy a connector for it. It's high speed by design. It's really designed for PCIe 5 and 6, and you can get very high lane counts from it, up to 16. The thermal architecture I find very good. Each form factor has very realistic and achievable thermal design targets. The density is foremost in all of these form factors in the standard, and the power budget is very generous as well. And of course, for device flexibility, this is the Enterprise Data Center Standard form factor now, not the SSD form factor. That means that you have lots of flexibilities with plugging in all kinds of other peripherals in there, like CXL devices, accelerators, maybe network devices, maybe storage class memory. So very versatile slot. And if you're interested in the relevant specs, at least for E3 specifically, there's the SFF TA 1002, 1008, 1009, and 1023 that you can refer to. So looking at the IBM Flash Systems portfolio, we currently have 3 main enclosures, high-end 9500, which is a 48 drive enclosure, a mid-range 7300 with 24 drives, and an entry-level 1U with 12 drives, 5200. And it can use either industry standard SSDs or what I'm going to be focusing on is the IBM FlashCore module, and it is an enterprise QLC SSD. It has compression and encryption at line speed and RAID assist. So we are able to offer this drive at a very competitive cost because of QLC storage gives us quite a bit cost reduction on the hardware. And this is a dual port active storage enclosure architecture. So why does the EDSFF benefit IBM Flash Systems? It has a greater power envelope, allowing for a more flexible design, more efficient use of space, and PCIe Gen 5 enables either fewer lanes to your drives, or you can enable higher bandwidth at the PCIe switch level. The connector architecture is much simpler than it was on U.2. And again, the slots are more useful for more things other than SSDs, so you don't have to work on all these funny slots for all kinds of peripherals. And if you were at Flash Memory Summit last month, and you looked at all the high-end cutting-edge drives out there, they were all E3. There's really no new stuff on U.2 anymore. So if you want the highest speed, highest performance, you can see the market, it really is jumping into the EDSFF form factors, including E3. So you really need a roadmap to be on that in order to remain competitive. So let's look at the SSD design methodology. Here's what the current third generation IBM FlashCore module looks like. And it's got an array of Micron NAND flash. It's got DRAM to address that flash, and it's got a FPGA for controlling the flash memory as well as providing an NVMe interface. And it's got MRAM to help with persistent storage that is tolerant of power failure, and capacitors for also tolerating power failures as well. So our design goals, what we're looking to do is convert this into the EDSFF form factor, specifically E3. We want to maximize our terabytes per rack unit, minimize the cost per terabyte, provide the high quality and reliability that our clients are used to, and utilize an FPGA specifically to achieve the compression, encryption, RAID assist, and future features. And if you hear our fellow Andy Walls speak, he's got a lot of computational storage features he's excited about coming over the next year or two. So let's look at the form factors of EDSFF, starting with E3.S. The E3.S is targeted for regular NVMe SSDs. It has a power budget very similar to the U.2 15 millimeter, which is a 25 watts. So that's where you'd want to be if you're just kind of creating ordinary SSDs. There's a E3.S 2T, which is double thickness, and that's targeted towards higher performance SSDs, storage class memory, CXL, and the power budget starts to get more interesting there. Up to 40 watts allows you to implement a lot of more interesting features in there. So just looking at the IBM FlashCore module, the E3.S single thickness is really too small for us. If we wanted to implement that, we'd be spending 2/3 or 3/4 of our space just with our FPGA and our memory, our DRAM memory, and not a whole lot more for actual flash storage. And the power budget's still too small. You know, we're looking at what can we increase, what can we add value in the space, and that's not really going to help us. So the 2T is interesting. It's close to the U.2 dimensions. It's about 1/4 inch wider and deeper than U.2. And it's got a very good power budget. It's 40 watts instead of 25 watts. That's a lot of room for growth there. So we'll just keep that in the back of our heads. Now looking at E3.L, this is the form factor that you'd want for most dense storage capabilities. And then there's a double thickness version of that that's for FPGAs or accelerators and computational storage. So FlashCore module kind of straddles those two spaces. We're a mix of both. We have some computational storage, and we want to be the biggest SSD out there. So if you don't need 70 watts of power, you're really losing half your density if you go to the 2T versus the just standard E3.L. And if you compare the E3.L to the E3.S 2T, you're really able to double your density by going to the E3.L because you can fit twice as many drives in a front loader. So what about E1.S? We did consider this. It comes in two sizes, mainly differentiated by do you need a heat sink for extra power or not. And the problem, quite frankly, is a 40 by 40 millimeter FPGA doesn't fit on a 38.4 millimeter form factor. So you could go to smaller FPGAs, but then you start running into issues with complex routing. You'd have to implement some exotic PCB fabrication techniques to get your signals out, which adds to cost. And then also when you go to a smaller FPGA, you have less IOs for your flash lanes. So you just look at all that wasted space. You could put flash memory there, but if you don't have enough lanes to drive it effectively, then it's not going to work. So just for completeness, I'll talk about E1.S as well. It's optimized for 1U servers. It comes in 5 sizes. I believe the first 2 sizes are sort of boot media oriented, and the rest, the use cases are caches, blade servers, edge servers, artificial intelligence, machine learning, and high performance applications. And some of these might operate in, they might be rear facing drives. They might operate in the high temperature, low flow thermal space, requiring that you can tolerate ambient temperatures of 50 degrees or more. And it's not really optimal for our high-capacity flash core module. I mean, these are really interesting form factors, but if we're trying to offer the most terabytes in a certain space, these are not exactly what we'd be looking for. So how would we lay out our current flash core module? And by the way, that's a rigid flex in between the two boards, so the boards kind of sandwich over on each other and operate in parallel in our form factor. So all the components, they transition over pretty easily to the E3.L. You can see the NAND array is, just moves right over. The controller, the DRAM, and the MRAM, they just move right over. And then we don't have to avoid that rigid flex area, so we can put components in between there freely without having to worry about being on the edge of our board. So definitely a feasible layout. So the challenge comes with FPGAs. So this is a 7.5 millimeter Z height, and our spec is optimal. I mean, the spec is optimal for basically ASICs and flash memory below about 2.2 millimeters in height. And it's because the spec requires the card edge be really close to the center of the stack up. I mean, it's off by 20 nanometers or something, but very close to the center. The problem is with FPGAs. With the one we're using, it's very close to 4 millimeters tall, so it's not just a tight fit. It's actually, you're out of your form factor if you use this, and you don't do anything about where your board is. So, and it's not just FPGAs that are the problem. You might have voltage regulators that are big. You might have big capacitors, supercaps. You might have inductors. So all these things are going to cause challenges for your physical design. So one solution is you could offset your PCB. Now that causes even more challenges to deal with. Now you've got a card edge you have to maintain in the center of the form factor, and your main PCB is offset. That's a problem. The LEDs, the standard requires that you put them in very specific spots on the front of your drive. That's a problem now. And the backside components, you're pushed so close, your PCB so close to the edge of your shell that you can't really have components there anymore. And then of course thermal design, with an FPGA, you're operating at very high power levels, and you've got a very, very thermally dense device there that you have to worry about. So you can shift your PCB. How do you mitigate that? You have to have the connector there. You could solder, board-to-board soldering. You could go with the rigid flex like we have in our current design. You could do some sort of a plug and socket and have multiple boards plug into each other like you might find in your cell phone. You can use an elastomeric connection. All of these cause even more problems. You've got signal integrity. Every time you hop an interface, that's a problem. Mechanical stability. What happens when you plug this several times? Does it break? Does it pop off? Does it bow? That sort of thing. And then these are all tiny dimensions. All this technology is very well established at higher geometries, but not at this small of a scale. And then the reliability, of course, for all these mechanical issues might go down, and your cost will go up. So the LED problem, here's an excerpt from the spec again. The LEDs are put in a place specifically to be right at a surface mount location on a standard PCB orientation there. So if you move your PCB up and down, well, you're out of your hole now. So if you're too high, then your PCB is obscuring the hole. If you're too low, then your LEDs don't even touch the hole. So you have to mitigate it through things like light pipes, maybe making a custom LED, do a board-to-board soldering to raise your PCB height, or you could try to sort of cheat and make the hole bigger, flare it or something so that you eventually get your light out of the holes. And then your backside components. Well, you'll notice in my diagram, we had a double-sided NAND flash before, and when we offset the board, well, your shell is now where your NAND needs to be. So as with anything, it's a trade-off. So you could move more components to the taller side of the board. You could thin out your case, or you could maybe offset your board just for the FPGA and then offset it back to handle your NAND flash. Another thing that's possible, I mean, you could do funny FPGA packages where they maybe mount on the same side as your die. It gets really ugly really fast. And thermal design considerations, yeah, the FPGA produces a lot more heat than an ASIC. So you have to think really carefully about your materials. Do you use standard aluminum? Do you go with alloys or copper? Do you put in some sort of heat spreader slug? You have to be very careful about your thermal interface material. That's like where the rubber meets the road. If you don't have a good thermal interface material, you don't have good thermal conductivity. And then what shape do your fins need to be to get all the heat off of the case as it gets air blown across it. And then so thermal simulations are a must. You definitely need some very skilled thermal engineers looking at how this is going to behave at a simulation level before you build anything, or else you're kind of doomed to fail. And of course, if you look at the SFF TA 1023 spec, which I'll just call 1023 from now on, it offers a lot of testing advice on how do you actually characterize and make sure that you've designed things properly. So let's look at enclosure design and thermal design. So keeping your SSDs cool. If you look at a typical 24 drive 2U U.2 storage server, you've got 24 SSDs running at 25 watts max. That's potentially 600 watts of heat generated just by the drives. Now if we look at what happens when we use E3.L, you could fit 44 SSDs in that space at 40 watts each. Well, that's nearly 3 times as much power. And then you have to worry about, well, where are you going to get cold air from for your CPU and all the things behind the drive? So that's a big challenge. So again, back to the 1023 spec, it does give you thermal design criteria for both the devices and the enclosure so that you can make sure you have a good design. And if you look at the picture here, the spec recommends that you operate in the level 3 area, the blue area, and I'll get into what these levels mean in a minute. But in a nutshell, you basically you design and characterize your enclosure to operate at a higher level than your devices that you're going to put in there. And these levels offer a sort of a negotiation point where if the enclosure builder and the SSD builder are different, you can sort of say what level you claim to support, and then when you put it all together, it just works. So the 1023 spec talks about an environmental setup you can use to test, and it's basically an airflow chamber with various temperature and airflow set points, and then a box that holds your SSDs or devices. And what you would do is just run various NVMe power states, different workloads, and collect the data. Just see what your worst case corners are, and then provide the charts that I'm going to show in a minute. So first characteristic you look for is airflow impedance. So the spec defines 8 airflow impedance levels, A1 through A8. The enclosures are tested with devices of different AFI levels to determine which levels they can support. You can impact this through fan design, ducting, and all that. And then the devices are also tested to characterize their AFI level. So the AFI is impacted by things like the device's shape. What does the heatsink fins look like? What do the vents look like? All that. And you want your airflow impedance tolerance of this storage server to be better than the AFI level of your devices. So the issue is mainly with fan efficiency loss. If you have so much airflow impedance that you can't get air through, then you're not cooling anything because your air is not flowing. So that's really the knob you can turn on the enclosure side is higher performance fans. And on the device side, or you can change the shape of the device or how it impacts the air that goes through it. So here's an example. You might have an enclosure in red here, which was characterized at an A4 level, and you'd always kind of round down to the next lower level for the enclosure, and then you have a device that's a A3 level, you round up for the devices to the A3 level, so that way you don't, if you're on the edge, you don't over-advertise capabilities. The max therm levels, this is the minimum airflow required at a given thermal design point. Again, there are 8 max therm levels. I don't think these correlate to the airflow impedance levels. There are different levels. Devices are tested to determine their max therm level, which hopefully is in the blue region, and the enclosures support devices at or below its max therm level, which is hopefully above the blue region just a little bit. Whoops. And so you can see here, here's a good level 3 enclosure with a level 2 device in it. And again, the enclosures, they round down their capabilities, and the devices, they round up their capabilities. So D-therm, they're the same levels. This is, if you had something like a service action, if you had somebody who pulled out a compute canister or a power supply, or you have a fan that's broken, or somebody pulls out a drive, your airflow profile is going to change a little bit. So you want to define what we call D-therm levels, which are lower power states that you can have on your drive. And they can be managed by the host, or they can be managed by the SSD. They're typically the NVMe power states that you'd use to implement these. The downside here is quality of service is impacted. So if you're trying to guarantee a certain amount of performance and you use these D-therm levels, then you're going to have to throttle down to something of a lower performance. So you might want to just over-engineer everything so that when you do have one of these service actions or degradations, that you're still providing the type of airflow you need to have all the devices running at max performance. So again, here's an example of maybe our enclosure gets downgraded to a level 1 thermal level, and your device is luckily also throttling down to a level 1 D-therm as well. So look at min ambient and max ambient. This is your documented approach temperature limits outside of which your device may be having problems operating. So the min ambient is the lowest approach temperature your device supports. Most of us aren't going to have any special requirement here, but the specs thermal curves only go down to 25 C, and if you actually want to test below 25 C, it's kind of impractical. You spend a lot of money on something that overcools your air, and nobody really operates there anyway for the most part. And some components might not even be qualified below room temperature anyway. Yeah, sure, you'd want things to operate at 0 C, but it's practically speaking, you don't do that. And so you basically change your min ambient if there is some reason that your device can't operate at a temperature that low. Maybe there's a dew point concern, maybe there's I don't know why you do this, but yeah, there may be reasons why you need to declare a higher min ambient. The max ambient is the highest approach temperature to your device, and it's in allowable ranges between 50 C and 65 C, and this is the point at which your throttling would occur, the point at which you invoke these D-therm levels. So I do want to point out, if you compare this spec to the ASHRAE spec, ASHRAE has ambient temperature levels from 32 C to 45 C. And this spec was really designed for SSDs in mind, to keep the reliability of the SSDs in mind. So if we're designing our enclosures to match ASHRAE specs, then I don't know why the spec wouldn't allow max ambient to be below 50 C. It would be really nice if we could say that we had a max ambient that matches these ASHRAE levels. So that's a gentle request there. Okay, the gap design considerations. So for E3 devices, the spec recommends you operate in the blue region again, and it also recommends a gap between devices of 1.8 millimeters. So, and there's lots of equations in the spec you can utilize. So example, at 35 C, you can see just barely a 2.5 CFM translates over to 1700 LFM. you can use the equation, you can use the chart. So comparing to a 7 millimeter U.2 device where you typically have a pitch of 12.5 millimeters and a gap of 5.5 millimeters, the LFM is much higher for the smaller gap than the larger gap. But if you're looking at a 15 millimeter U.2 device, the pitch is 16.5 millimeters and the gap is 1.5 millimeters. It's very similar to what is being recommended here for the EDSFF spec. So definitely the channel velocity varies depending on the gap between your SSDs, but it can be calculated easily. Airflow impedance is not totally easily calculated, but you can definitely decrease your airflow impedance with a wider gap if you need to. So just looking at where IBM thinks things are headed, we're recommending a 3 millimeter gap between devices to get optimal cooling. And if you did that, if you plugged in a 2T device in a pair of E3 slots, you'd have a slightly larger gap of 4.2 millimeters. So really quick, what do carriers look like with E3? We think it's pretty trivial to design a carrier that can support both short and long devices. And so you can see that it's easy to fit them in. The only challenge here really is getting your LEDs translated out to the front of your carrier bezel. So you'd have some sort of light pipes or something to get them out. And then similarly with double thickness, you basically reuse the same design methodologies. And one interesting thing about the form factor spec is that the screw holes and the LED holes are all in the same place with regard to one of the sides of the devices. So that's very handy. You can reuse some tooling there. So there may be things like maybe the tray, you could use a standard thickness tray and hook it up to a double thickness bezel, things like that. But again, yeah, you can fit a short or a long in the same carrier if you want to. So let's step back. There's a really nice white paper by Bill Lin, Paul Kaler, and John Geldman here. And there were several enclosure configuration options explored. So there's the highest density, just pack as many as you can in there. There's a slightly lower density where you have more airflow to cool those things like CPUs and backside peripherals and all that. And then there's a combination where you have a higher airflow around the drives, plus you have some of these double thickness devices like CXL, storage class memory, and accelerators. And so lots of options here. And definitely I'll quote this exactly. The flexibility of the E3 form factor gives platform architects a wide range of options when it comes to supporting multiple system use cases. The ability to optimize around either density, host bandwidth, system power, or device type makes E3 an ideal choice for the platform architects and system designers. So that's really in a nutshell why we like it. Definitely, there's a lot of opportunity to put in these double thickness devices that may add value to the client. So at IBM, we're looking again at our 3 enclosure types: the 1U entry level, the 2U mid range, and the 4U high end. And we want to maintain a common design for all of IBM storage brands. And we want to focus that around the E3 small or large as primary design point. And we want the flexibility to support both E3 and E3 2T devices in the same enclosure. And of course, meet the thermal design requirements based on what we think the slot-to-slot pitch is going to be. So zooming in on the 1U concept, 20 drives is possible. However, if we wanted to maintain this 3 millimeter gap that we think is optimal, it's not really possible for all slots. You can, if you wanted a true even gap, you'd go for 2.4 millimeters. However, if you started doubling up using 2Ts in those slots, you'd have mismatched gaps of 2.4 and 3 millimeters. So it gets a little funky there. Looking at the 2U, it's pretty, you can see it's fairly trivial to design a good 2U server around this concept. You can have a 2U enclosure with dual redundant 2U half-wide canisters, compute canisters with a side-by-side configuration. And each canister can support up to 12 DIMMs per socket, up to 4 PCI Express slots in the back, hot pluggable, replicable E1.S boot drives, hot pluggable and replicable power loss protection, and 1+1 common redundant power supplies. And on the front end, you can have the 32 E3 devices and 4 E3 2T devices, as in the concept from the white paper. And 4U, similarly, can use 2U canisters with a top-bottom configuration, and each canister would be basically a dual socket server with 12 DIMM slots per socket, and up to 8 PCIe slots per canister. So effectively, looks very similar to just two 2U stacked on top of each other, except you get a little bit more room for PCIe slots out the back. And again, hot plug replicable E1.S boot drives, hot plug replicable power loss protection, battery backup units, and 2+2 common redundant power supplies. And that way you get the 64 E3 devices and 8 E3 2T devices out the front. So in summary, SSD and storage server suppliers really need to have an EDSFF roadmap to stay competitive. It's clear just from looking at the high-end SSD offerings that are out there that they're really going to be in the EDSFF space, and U.2 is dying out. It'll still be around, but it's not going to be there for the highest performance stuff. So I did present some design concepts for SSDs and enclosures. I think we can fit an FPGA into an E3.L form factor, despite all the challenges. That'll help us maximize density. And the 1.8 millimeter device gap in the in this standard is, I find that to be an example, but not really ideal for all use cases. If you did look at the Flash Memory Summit's vendor floor, you'll see a lot of people had a lot of designs that didn't have a 1.8 millimeter gap. So not everyone needs that gap for maximum enclosure density. You may have some more compute-focused servers with less storage in the front. And if you need to, you can adjust the airflow impedance by adjusting the gap. So that's another knob that you can turn. So thank you all for coming. If you have any questions, please let me know.
I have one question on
Okay.
slide 87. Did you have a mix of form factors in the server? So 64E3 and 2T as well?
Yeah, so the question was, is there a mix of form factors? So yes, there are eight slots that are dedicated to 2T. They've got, the rails are designed for 2T. Everything else is standard thickness. And if you needed to, you could put a 2T in one of those other slots. You would just be wasting a connector. But yeah, it's designed to have.
Does that give you an advantage then? Does it having a form factor? Could you have more E3 slots?
You could. The question was, is it an advantage to have a mix of form factors? And you could design this to just have all single standard thickness slots and not mix them. But for where we think IBM can add value to the client, we think that having some slots available for accelerators is going to allow us the flexibility to add value. So we've designed it specifically for some dedicated double thickness slots.
One of your charts where you showed the 1023 curves for AFI terminal levels, and you talked about the device having certain AFI level, and then the storage has not only, and your goal is obviously to have the storage be better, but then you want to minimize the gap so you don't what kind of trade-offs do you typically are available to the, say, on the enclosure side to reduce that gap? What do you typically look for?
So what are the trade-offs you could have on the enclosure side to reduce the gap between your device's AFI and the design of the enclosure? So, yeah, it is optimal if those levels are very similar, and certainly your fan RPM is a big part of that, so you can control how much pressure is applied by how strong your fans are. The gap between devices is another knob you can turn, and those are all enclosure things you can do. If you have control over the device like we do, you can change the geometry of the device. Maybe you can add extra slots in it, heatsink slots, or I guess features on the heat sinking portion of the drive so that you allow more air to go across it. So those are the obvious ones that come to mind when I think of how do you optimize. Because yeah, you would want your enclosure to not be over-engineered, because one big issue is acoustics. If you've got the best fan out there, I mean, you don't want it, people don't want to work around your equipment anymore, even with hearing protection. They just don't want to. They don't want to be in the room. So, all right.
So we can follow on to that. You showed on slide 23 a typical 2U server with 24 SSDs and your bigger one running 44 SSDs. The next slide talks about, well, you got to go run all your various workloads against your various NVMe power states. Are you designing your thermal solutions to handle worst case workload every single drive and simultaneously sustained? Or do you pick some sort of activity factor reduction off that point? And if so, any comments on what that might be?
Well, the goal is to tolerate multiple problems on your enclosure: high altitude, high temperature, some fans offline. That being said, it's very difficult to do that. So we typically expect that if it's a service action where a user is pulling out a thing, maybe we can tolerate 10 minutes of a device getting kind of hot. We assume that they can replace the device in less than 10 minutes, that sort of thing. But we do try to design for those worst case scenarios. And when you talk about sustained, I mean, you know, I wouldn't say you'd run it years that way, but we don't want to, from IBM's perspective, we don't want it to reduce this quality of service because of a service action.
Yeah, I saw this originally in the laptop world, which is if you run worst case workload for CPU and graphics and Wi-Fi and storage and DRAM and everything else, your laptop would be twice as thick mitigating worst case thermal. So they just don't even try. They have a thermal design profile that there are some of the word is essentially tossed around TDP, which is way less than the sum of all worst cases combined. And I was just kind of curious if that methodology works your way into some of your thermal design practices.
I mean, so if we think about the standard allowing us 40 watts to use, we're not planning on going up to 40 watts on all devices at all times. So we're actually going to try and design to a much lower power level so that we're not operating at the worst case of everything. So we're reducing our power requirements per slot, but we're still planning on having it run at kind of worst case within our reduced level most of the time. So.
Any comment on how much you derate by it, or is that? It's okay.
Well, none of this is actually in a shipping product, so I don't think I can comment either way. So. All right. Oh, John?
How important is latch design?
Latch design? Like on the carrier?
Yeah.
Well, this isn't one of my specific focuses, but I do realize you can jam your latches pretty easily if you don't design it properly. So we do run into a lot of what-if scenarios of people plugging things in harshly or incorrectly. And certainly if you push your latch in and you're not fully engaged, you could separate your enclosure slot and pop all your drives out. So yeah, it's very important in that respect.
How about to airflow?
To airflow?
Go to slide 33 when you're talking about.
Sure.
Picture your latches there. No? Your numbers changed, sorry.
Oh, they did? Oh.
There you go.
Yeah, so you do need to take into account how much air is going around the edges of the drive. So yeah, if your latch puts things in the airflow path, then that changes your AFI a little bit. It gets things a little bit off of what your equations might recommend. So a lot of what's in the 1023 spec is kind of theoretical based on the gap between the large surfaces of the drive. But yeah, there are effects that you get through the thin edges of the form factor where your latch might be, or where your drive is interfacing with the slot.
So one more. Have you looked at the relative costs of the complexity of FPGA in a 1T versus chip on board?
We just know generally chip on board is going to be more expensive in terms of your board process, your attach process, and you'd really be using, instead of a standard a PCB material, you're using basically a packaged substrate as the entire device, and that's very expensive. So yes, it can be done, and that's the way we would do it, but I think that the cost is a problem there.
So back to John's question on airflow connector, even the way you guys have your rail done, it doesn't allow any opportunity for any airflow inside of the device. With the ventils, you're making the assumption all air is going on the outside, is that?
Well, so this is kind of a simplified. If you're talking about this flat face here that has no airflow, that's actually not real. This is just kind of a quick and dirty mock-up. There would be air going through the front of that carrier bezel to your device. That was just kind of simplified concept. Yes.
When you talk about the E3L 1T, challenges and offsetting PCB, in terms of backside components placement and not having space enough, approximately how many components are we talking about on the back together? Like more than 8 or?
Well, if you look at our current flash core module design, we've got 10 flash memories on each side of the board. So there's that, and if you wanted to do a double-sided clamshell of the DRAM, that's another 5. So already 15, 16, 17, that range. Okay. Any other questions? All right, well, thank you all for having me. I really appreciate the opportunity to speak today, and I hope you all have a really great conference.